Panoptic scene completion, or PSC in short, aims to predict a complete 3D scene, represented as a voxel grid, including semantic labels for occupied voxels and instance-level segmentation to group individual objects. While PSC was introduced using LiDAR modality, methods based on camera images remain largely unexplored. Therefore, vision-based panoptic scene completion could so far only be accomplished by tediously clustering the output of semantic scene completion methods, which only predict the semantic labels of occupied voxels. In addition to the lack of visual PSC solutions, recent transformer-based methods for semantic scene completion utilize a fixed set of learned queries to model objects within the scene. Although these queries are randomly initialized and then updated with image context during training, they remain static at test time, limiting their ability to dynamically adapt specifically to the observed scene. To address these limitations, we introduce IPFormer, a 3D vision transformer designed to address panoptic scene completion. IPFormer directly initializes these queries as instance proposals from image context, which preserves context adaptivity even at test time, effectively aggregating directed features to improve PSC performance. Technically, IPFormer starts by inferring 2D image context and a depth map, which are both utilized to generate contextual 3D representations, namely a 3D feature map and initial voxels. During initialization, the voxels are decoupled by sampling them based on their visibility, to eventually generate instance proposals and voxel proposals. Note that instance proposals are derived solely from visible voxels. This visibility-based sampling strategy is grounded in the principle that all potentially identifiable objects within the observed scene must exhibit a visual cue in the camera image to facilitate their completion. Based on this context-adaptive initialization, we established directed feature aggregation at train and test time, forming a robust reconstruction signal that significantly improves semantic classification, geometric completion, and instance identification. During encoding, first, the voxel proposals are locally and globally encoded to generate voxel features. Then, we attend the instance proposals over these refined voxel features to generate instance features that correlate with all voxels. The decoding step aims to finally reconstruct the scene. More specifically, we follow a two-stage training strategy in which the first stage uses only the voxel features to solve semantic scene completion. This stage effectively guides the latent space towards precise semantics and detailed geometry. Subsequently, the second training stage registers individual instances within the semantic features to finally align voxels and instances, which results in a complete panoptic scene. In summary, our quantitative results show that IPFormer exceeds all baselines in overall panoptic metrics, PQ and PQ dagger, and achieves best or second best results in individual metrics. Moreover, our method directly predicts a full panoptic scene, resulting in a significantly superior runtime of 0.33 seconds, thus providing a runtime reduction of over 14 times. Ablation studies successfully evaluate the effectiveness of our key components, showing that context-adaptive instance proposals, sampled from visible-only voxels, combined with a dual-head architecture and a two-stage training strategy, lead to superior PSC performance. Qualitative results show that IPFormer effectively delineates individual objects, while the baselines often struggle with distant objects that are close to each other, such as cars. Similarly, vehicles with orientations that differ from those typically encountered on the street pose challenges for most baselines. These models often struggle to effectively identify semantic instances while maintaining geometric integrity. In contrast, IPFormer excels at identifying individual instances, inferring semantics, and reconstructing geometry with exceptional fidelity. Notably, dynamic objects that exhibit trace artifacts in the ground truth data can be challenging, but they are well delineated by our method. And even for extremely low-frequency categories, such as the person category at 0.07%, our method demonstrates visually superior results. Additionally, we derive saliency maps through gradient-based attribution, which provides insights on where an individual instance mainly retrieves context from, highlighted in green on the camera frames. Our introduced instance proposals effectively adapt to scene characteristics by guiding feature aggregation that substantially improves the PSC prediction. In contrast, non-adaptive instance queries sample image context in an undirected manner, causing misclassification and geometric ambiguity. In conclusion, IPFormer advances the field of 3D panoptic scene completion by leveraging context-adaptive instance proposals derived from camera images at both train and test time. Our findings serve as a promising foundation for future research in holistic scene understanding and downstream applications like autonomous navigation.